Up to now, we found how to analyze resistive circuits. We found two methods, nodal and mesh method. In nodal method, we are looking for finding what? In nodal analysis, we are looking to find voltage of nodes. Yeah. If we find voltage of the nodes, that means we know all voltage and currents of all branches. But in mesh analysis, we are looking for finding current of all meshes. If we find current of all meshes, that means we find all currents and voltage of all branches. Last session, we saw if we have a resistive circuit with dependent and independent source, no matter how much complicated this circuit, bunch of resistors, maybe 100, bunch of dependent and independent sources, no matter how many branches are inside, we can simplify that complicated circuit only with one voltage source and one resistor. Yeah. The only condition is they should be linear. Yeah, resistors should be linear. Or we can replace these complicated circuits with Norton equivalent. One current source parallel with one resistor. How do you find our equivalent, resistance equivalent from the ports we are looking to the circuit? What was the general method? The first step is, what should we do? Exactly. We should set the all independent sources to 0. That means if we have voltage source, we should short circuit it. If we have current source, we should open circuit it. After zeroing all independent sources, we should see if we can find the equivalent resistor by series and paralleling the other resistors, we do it. What should we do? Exactly. We should apply one V-test. We should apply one V-test and find I-test. That means the equivalent resistor we are looking from this port is proportion of VT over IT. Okay, that's general method. Sometimes it's easier for you to just simplify the circuit by paralleling and series the resistors. If we have dependent sources, what do you do if there is a dependent source? Can I use parallel and series to find? No. If we have dependent source, we should apply VT and find the relationship between VT and IT. That's the general method to find equivalent circuit. How about VT, Thevenin voltage? How do you find it? How do you find Thevenin voltage? Exactly. The Thevenin voltage is open circuit voltage of these port that we are looking at. Yeah. We should consider this current is 0, find this voltage, we call it Thevenin voltage. IN, Norton current, How do we find Norton current? Yeah, if we find Thevenin voltage, that means we already found IN. The relationship with IN is VT over RT. Yes. No, if we want to find IN directly on the circuit, what should we do? Exactly. We should short circuit these ports that we are looking and find the current that goes from these short circuits. The current is IN. We saw some examples together last session. There is another general way to find both R Thevenin and V Thevenin or I Newton together. Yeah. If we have dependent source, it's easier to not zeroing, not setting the independent sources to zero. You just need to apply VT, IT, but the relationship between VT and IT would be like this. Yeah. There is a coefficient to IT plus a constant. This constant is V Thevenin. You know, previously when you short circuit the independent sources, when you were looking from here, the relationship between VT and IT was only a coefficient. It was zero here. Why? Because this is effect of independent sources. So if you don't set the independent sources to zero, that means we have a constant here, yeah, which is equal to Thevenin voltage. And this is R Thevenin. That means if you apply VT and find the IT, you can find the whole together. But sometimes it's easier if you don't have any dependent sources. It's easier to set independent sources to zero, find easily R Thevenin, but by paralleling and setting the resistors and finding V Thevenin as the open circuit voltage of here. If you don't have dependent sources, sometimes that's easier. We have different methods to find it. You should find by yourself. You should have intuition which method is easier when you are looking at the circuit. Suppose we have this circuit and we want to find the equivalent Thevenin from this port, from the X. Since we have dependent source, we cannot use paralleling and setting the resistor. We should apply VT and find the relationship between VT and IT. You know, as mentioned earlier, when we have dependent source, it's easier to find R Thevenin and V Thevenin both together. We apply VT, there is a circuit, you know how to analyze it. We can use nodal or mesh analysis. Yes, for nodal analysis, I can consider here ground. I have only one node here, another node here. For mesh, I have one, two, three meshes. So it seems nodal analysis is easier. If I consider this node as a ground, voltage of this node is how much? VT, yeah. Here is ground, here is VT volt higher. So I can consider here VT. If here is VT, how much is the voltage of this node? 5 volt higher than the negative terminal, which is VT plus 5. I can consider these two nodes as a super node and apply the KVL. That means I should put my hand here. How many branches are connected to this node? One, here, two, three, four. Yeah. One, two, three, and this one, four. This current is coming in minus IT. This current is going out 5X. And this current VT over 90. How about this 20 ohm? I didn't write the current of 20 ohm, right? When you are writing here, you should consider IT, and when you are writing here again, you should consider current of this resistor, and when you are writing KCL here, you should consider again. If I suppose the current is going down, when I'm writing KCL here, it's negative, and when I'm writing KCL here, that's positive. That means they will cancel out each other. So I should find the relationship between Vx and Vt here. I'm looking for a relationship between Vt and It. Vx is extra here. I should omit it. How should I do that? Find the relationship between Vx, It, and Vt. What's the relationship between Vx and Vt? They are the same. So I can write Vx is equal to Vt. So this is a relationship between Vt and It. As we mentioned earlier, Vt is alpha It plus beta. How much is alpha? 96 over 19. We call it as R and there is no constant, which means V is 0. We have two most commonly used circuits here, voltage divider and current divider. If you have two resistors in series, the voltage across each of them is proportional to its value over the sum of the resistors. That means if I have two resistors in series, which one of them is much more bigger than another one, I can easily omit the smaller one. Yeah. If I apply 100 volt to these two series resistors, how much is the voltage? Let me consider this 9. How much is the voltage of this resistor? How much? Yeah, we can easily use the voltage divider. That's the value of this resistor over sum of the resistors multiplied by the voltage source. It's 90 volt. When we have 90 volt, how much should be here? Only 10. Yeah. That means when you have two series resistors, the one who is bigger consumes more voltage or consumes more power. We have more voltage drop across that resistor. How about when we have two parallel resistors? We have a current divider. If we have two parallel resistors, current prefers to go through which resistor, the bigger one or smaller one? Prefers to go through smaller one. When we are calculating the current of I1, we should write the resistor we are not looking for, which means R2 over the sum of them multiplied by current source. So if I have 1 ohm, again 9 ohm, and here I have 10 amp. How much is the current of this resistor? 1 ohm. The resistor we don't want, 9 over the sum 9 plus 1 multiplied by is 9 amp. This current is 9 amp. This current is 1 amp. How much is the equivalent of these two parallel resistors? The equivalent of 1 ohm and 10 ohm. Suppose I want to replace these two resistors with one resistor. How much the value? How much? 10 and 1, yeah. 10 over 11. Yeah, almost point. Yeah, which means almost 1 ohm. Yeah. When you are paralleling two resistors, which one of them is much more bigger than the other one, we can consider the parallel is only the smaller one. Yeah. Almost 1 ohm. The result should be smaller than both. Yeah. When you calculate the exact value, it should be smaller than both. But when one of them is bigger than the another one, much bigger, for example, 10 times, we can consider the paralleling these two is almost the smaller. How about when when we have two resistors in series, the bigger one, yeah? Because the equivalent is sum of them, and if one of them is 10 times bigger than the other one, the equivalent is the bigger resistor. Okay, I have a really good exercise here, which I added this exercise today. I think you don't have it in your slides. Okay, but I found it really interesting, so I added to check your knowledge. Okay, we have a circuit here. At first, they ask how much is the voltage VB minus VR across these 50 ohm resistor. The first question, how much is current here? If I have two circuits connected together, Do you remember cassette? Yeah, it was kind of super node, which means if I consider some of several nodes as a cassette, the all incoming current and outgoing current should be equal. Yeah, I can apply KCL to a cassette, which means if this is I1, this is I2, I1 should be equal to I2. Yeah, that's cassette. How about that circuit? I can consider these whole as a cassette. Yeah, yeah. I can consider these nodes as a cassette. And there is only one branch or one wire is coming. In one wire, can we have both incoming and outgoing current? No way. That's zero. Yeah, exactly, it should be zero. When you are connected a circuit, it should be kind of loop. Yeah, the current should be in a loop. If you don't have loop, you don't have any current. So this current is zero. Why? If you apply, if you consider a cut set here or here, there is no way for the current to come back. Yeah, so the current should be zero. If current is going to that way, it should be another path to coming to this way, which we don't have. If this current is zero, that's easy to solve. Yeah. How do you solve this circuit? We are looking for VBR. I can analyze these two circuits separately. Yeah, because there is no current here. I can omit this wire. So I have a circuit here and another here, which they are related together by what? By a dependent circuit. They are related together by this dependent circuit. So for this side, I'm looking for IB. How can I find IB? Can you repeat again? Exactly. We can do that. Yeah. Yeah. If we cannot do that, suppose I don't know anything about paralleling and setting the resistors. Yeah. Based on the method we know, we should solve nodal or mesh one, two meshes. How about node? If I consider here ground, here is 1 volt, here is 1 volt, and I have only this node. Yeah. I will solve it by two methods. So we have 1 volt here. Any 5, 50. Our systematic method is using mesh or nodal. Which one is here? Which one is here? Nodal, for sure. Two meshes, one node. Here ground, here 1 volt. Here we have E1, for example. E1 minus, applying KCL. E1 minus 1 over 25 plus E1 over 50 plus E1 over 15. should be 0. Multiply by 50 to even 2 plus 1 plus 1. 4 even should be equal 50 over 25 is 2 multiplied by 1 is 2 should be go to other side is positive 2. 6 by 6. No, they are 50. 50 over 50 is 1. 50 over 51. 1, 2, and this is 2, 4. Even is 2 over 4.5 volts. So IB is even over 50 is 0.5 over 50. Yeah, exactly. 0. The another way your friend recommended, he said we have 250 ohm, they are in parallel. 250 ohm in parallel means how much is the equivalent? 25. 25 plus 25, 50. This source is looking to a 50 ohm. How much is its current? 1 over 50, which means 0.02. This current is coming here. And here we have one current divider, like the previous slide we saw. Yeah, 250 ohm are in parallel and we have a current. Since both of them are the same, the current should be divided by 2. Yes, IB should be, how much is this value in milliamp? If you want to say 10 milliamp. This current is 10 milliamp. And for the other side, 100 IB. How much is VBA? Yeah, VBA is voltage across the 50 ohm, which is based on Ohm's law. VBA is this resistor multiplied by the current going through that, which is 50 ohm multiplied by 100 IB. How much is IB? 1 over 100, 100, that's 50 volts. So VBA is 50 volts. The next part is asking if we change the 1 volt to 2 volt, this voltage source, how much would be VBA? No change. Why? Okay, let's see. If I put this 1 volt, 2 volt, what will happen? How much resistance I'm seeing from the source? It was 250 ohm, equivalent 25 plus 25, 50 ohm. When here I have 2 volts, that means current should be double. Yeah. This current, shall I write in another? Let me draw another schematic. Schematic here. So how much resistance I'm seeing from this source? 50 plus 50, 50 parallel 50 is 25 plus 25, 50. 2 over 50 means 0.4 amp or 40 milliamp. And it should be divided by 2. This is IB. We should multiply IB by 100, which this current should be 2 amp, multiply by 50. This voltage would be 100 volts. You know, we change 1 volt to 2 volt. What happened to this voltage? It's double. If we change 1 volt to 10 volts, what will happen? Exactly. That's linearity. Yeah, we call it as a linearity. If you have a system, we will see it in the next course. If Y is alpha X, yeah, this is a linear relationship between Y and X, input and output. If I consider VRB as the output and these voltage source as the input, I can find VRB if I write this as V in and VRB as the V out. VO is going down here. So VO is 50 V in. Yeah, there is a linear relationship between input and output. We call this circuit a linear circuit. Which one? VPA. How we calculate this one? Here or here? This one? Same as this here. How much is IB? 0.02. If we multiply it by 100, how much is this current? This one? These two are parallel. Yes. What's the equivalent of them? 25. 25 with 25 is 50. That means I have a circuit here like that. Yeah. How much current is coming from the source? 2 volt over 50, which means 0.04. So this is 0.4. It's coming from this source. Yeah, it comes here and it sees 2 parallel resistors. It should be divided by 2 because they are similar value. Which one? This one? Yeah. Summation of these two currents should be this one. Yeah. Because this is divided by 2. Okay. Have you ever seen you got electrical engineering? Yeah, you received your BS. Have you ever seen these model? Do you know what is this? Haven't seen ever? What's that? That's exactly. That's linear model of a transistor. Yeah. That's core of active devices that we use it to amplify circuits. Yeah. Here we have an amplifier. We applied 1 volt here. How much we have here? 50 volts. We amplify the input signal by 50 times. Yeah. We call it active device, which means they are capable of increasing your input voltage or power. The last one, if we connect a resistor between B and A here, how much should be the RL to get the maximum power from this circuit? Here is why Thevenin and Norton equivalent is really important. Let's explain like this. We have a complicated circuit. We don't know what is inside. Yeah, I took all of these uh, network and I'm gonna put one Thevenin Norton as the equivalent. Yeah, here is B, here is A. I can do that, yeah, because I have only independent, dependent, and resistors, all linear. You know, we can, independents are not linear, we call it as the inputs of the circuit. That means linear elements with independent sources, which are inputs. So if I connect one RL here, how much should be the RL to get the maximum power? How much? Exactly. They both should be the same, but how? Okay, let me find the power of RL. What's the power of a resistor? IV, yeah, or we can write V2 over R or RI2. Which one is here for you? How much is the current in this loop? How much is the current? Exactly. V Thevenin over R Thevenin plus RL. I is V Thevenin over RL plus R Thevenin. Yeah, this is the current going through this loop. Okay, P RL is RL multiplied by I squared. VT over if I want to draw PRL over RL, how should it be? If RL is 0, how much is the power? 0. If RL goes to infinity, how much is the power? Exactly again, 0. That means this should be something like that. Yeah, we have power in the middle and again 0 at the end. How much is this peak? Based on your mathematics, how can you calculate this point? We should find the derivation of power regarding to RL and force it equal to 0 to find the way the slope of this curve is 0, yeah? If we do that, it should be RL should be equal to RTB. That's easier, I think. Derivation of this equation. And how much is the power? That's the maximum power. How much is based on the formula? These are equal RL, yeah? That means 2RL squared, 4RL2, one of them is should be simplified by RL, which is P7 over 4RL. This is the maximum power RL can get from this circuit. Now, what should we do for that circuit? They are asking how much should be RL to receive the maximum power. 550. What's your strategy? Yes, that means we should find Thevenin equivalent. Yeah, exactly. That means, okay, we are looking from here, we should find the equivalent resistance of this circuit. Yes. Now, what we have here, we have only one independent circuit and independent source and one dependent source. We set the independent source 0, so we have 25 here. 50, 50, IB. I'm looking for R equal from A and B node. Can I use paralleling and setting these resistors? Can or cannot? I can not. Why? We have a dependent source. Yeah, when we have dependent source, we cannot parallel and series resistor together to find the equivalent resistor. What should we do? Test and test voltage and current test. VT, IT. There's no current here. Yeah, I can omit this way. How much is IB? Yeah, that's zero. Why? Okay. I consider here zero. Write a KCL here. E1 over 25, E1 over 50. E1 over 50 should be equal to zero. The only answer is E1 should be zero. E1 should be zero. That means IB is zero. If IB is zero, this current source is also zero. When it's zero, that means I can easily remove it. I have only 50 ohm from here. Yeah. That means equivalent resistor is 50 ohm. Even we remove it, that means we open circuit it. So RL should be equal to R equal or R Thevenin, which is 50 ohm. Hmm. Right now, that's okay. I will calculate. Did you get the whole concept for the last exercise? I think that was one of the most beautiful practice that you could do to find equivalent models and its application. Yeah. Which formula? This one? How I find this one? This one? Okay. Here in this point, RL is equal to R Thevenin. That means here I can replace R Thevenin by RL. Yeah. Because in this point, both of them are equal. They are the same. So here I have two RL. If I square, that means 4RL squared. Yeah, I have 4RL squared here, 1RL in numerator. Yeah. I can simplify one of them, and I have only one RL in the denominator. That's okay. Yeah, I think it's a bit messy there. That's my problem. Yeah. Okay, we want to take a 5 minute break, and after that we continue with new topic. Okay, we have two topics to finish this chapter. One of them is superposition. What does it mean? When you have a resistive circuit and you have different independent sources, you can find any voltage or current of any branches by considering effect of each of these independent sources separately. Yeah. For example, here we have two independent sources. Since this circuit is linear, yeah, you can consider. I consider only once these independent source. I omit this one, remove it. So removing the current source means we should open circuit it. So I calculated the output voltage VO, and another one I take IS and remove VS and calculate VO2. That means if I add VO1 and VO2 together, the effect should be the same when I'm I have both these two independent sources together. Okay. Superposition means you can consider the sources separately or together. Since the circuit is linear, at the end, the result won't change. Yeah. The result of calculating VO while you are considering these two independent sources concurrently is the same when you are calculating them separately and at the end add the result together. For example, we have this circuit. We want to find Ix. Let's see if we don't know about this superposition. How do you find Ix? Mesh or nodal? It doesn't matter. If I consider here ground, here is 10 volts, here is 2Ix, so this is the voltage zone. So I need to apply KCL at this node. That means I need to write only one relationship. How about the mesh? I have one super mesh. I know this current. So again, I need to write one relationship. That means one KVL in this loop. Okay, we will do it after this. Use superposition. How many independent sources do we have in this circuit? Only two independent sources. This is dependent. So I consider once these independent source and set this to zero. Another time I set this voltage source to zero and consider this current source. Okay, if I set this current source to zero, which means I should open circuit it or remove it. If I remove that, I have this circuit. I can apply KVL only. I have one mesh here. Apply KVL, find Ix. I write it as Ix prime, yeah, because I omit this current source. I need to find Ix prime. Another time I omit this voltage source. I find Ix second. I add these two, which means it should be Ix. I write the KVL. I find Ix prime. Another time I set these voltage source to zero, which means I should short circuit it. I have this circuit, apply KCL at node V second. And I can easily find I second. So I prime plus I second should be Ix. If I solve this circuit considering these two together, the result should be the same. Yeah. Can you do by yourself? I wanna yeah. Solve this circuit, find Ix. No. We explain superposition. You use nodal or mesh analysis. Yeah. I wanna see can you solve it really fast or not? That's kind of practice. If you learn how use nodal and mesh analysis, after that everything would be really easy. The other, that's only concept. We just zero ones here, another time this one, and apply nodal and mesh analysis. Didn't you right? Is it easy for you or is it easy for you or you find it a bit hard? Fine. Okay. You are writing KCL at this node. E1 minus 10 over 2. Oh, what is this? I know. You wanna assign the voltage here. Yeah, here is ground. Here should be higher or lower. Why? No. We are talking about this node. Yeah. Yeah. You want to assign the voltage to that node regarding to this dependent voltage source. Here is ground. So this side should be higher as a voltage or lower. Why higher? I know, but it can be negative.
How do I know?
How much is this node?
Here?
Yeah.
It's 10.
Why 10? Why not minus 10?
But this minus
Exactly. The positive terminal is in the top.
Mm.
So if the negative terminal is 0, the positive terminal should be 10 volt higher.
Okay.
So that's why you consider here 10 volt.
Yeah.
If here is 0, here should be higher. How much? 2ix. That
So
means the
10.
voltage of this node should be 2ix.
Okay. But okay. Oh, okay. So here it's less.
So what is this?
This is what I mean. Like this line of the.
No, you know, this is voltage here. How did you write KCL here? You wrote E1 minus 10 over 2 ohm. That's the current of resistor. Here we have a resistor. Voltage of the left side is E1. Voltage of the right side should be
Minus 2i
by minus.
because this is higher.
So here is ground, so here higher. That means it should be 2ix, not minus 2ix.
But like here,
Yeah,
should I do it too?
yeah. You know, you should assign here, you should write 10 volt. Here you should write 2ix. When you are writing current from E1 from the this node to this node, you should write E1 minus 2ix over 1 ohm.
And they use 10 and only 2 meshes, 1 mesh on the left. The right.
Why two mesh? You know, if you write two meshes, you know, how much do you want to write the voltage of current source? You want to add V, yeah? You should write V. That means you should write minus 10 volts plus 2ix plus from here to here V should be 0, yeah? That means you are adding V and you should solve it. And again here minus V plus another current you should add here. Yeah, plus 1 I2 plus 2ix should be 0. You know what I mean? You have ix, I1, V, three equations. But if you consider here ground, you have this voltage, 10 volt, this voltage, 2ix, and you can easily write. Okay. I write one KCL here. You know, I can write the consider here as E1, but try to use the variables you have on the circuit. That's easy. If here is ground, how much is here? V volt, yeah? I can consider this variable as E1 or V. It's only notation. It doesn't matter. So for me, it's easier to consider here V, here 10 volts, here 2ix. So if I apply case here, I have V minus 10 volts over 2 plus V minus 2ix over 1 minus 3 amp should be 0. Okay, I have one equation, two variables. I should find a relationship between V, another relationship between V and 2ix. Where is ix? Ix is current of this resistor. Based on Ohm law, ix is, how much is ix? Exactly. Exactly. 10 minus V over 2. I could write here this one as minus ix. It doesn't matter. So I have 1.5 V. minus 2ix, which I can write 10 minus v minus 5 minus 8 should be 8. 2.5v should be 18. 18 over 2.5. X is 25. This is 5. 25 minus 18 is 7, which is 1.4 amp. See, the result should be the same because all elements are linear. Okay, another example, we want to calculate VO using superposition. Yeah, we have how many independent sources do we have here? We have two, yeah, 10 volt and 5 amp. We have two independent sources. First, we set 5 amp current source to 0. If we set this current source to 0, which means we should remove it because that's current source and we make it open circuit. So we have this circuit, I'm not explaining anymore because that's two mesh and 1, 2, 3, 4, 5 nodes. You know how to solve it. We will solve and find VO1. Another one, we are gonna set 10 volt to 0. We set this 10 volt to 0. That means we should make it short circuit. We reach to this circuit and analyzing this circuit, I think based on the examples we had, shouldn't be really hard for you. And again, we will find this time VO2. See, the last time we called this variable VO1 when we omit current source. This time when we omit 10 volt or voltage source, we call this variable VO2. If we add VO1 and VO2, we have VO in general. In general means considering both 10 volts and 5 amp voltage and current sources together. Another topic is symmetry. Sometimes in the circuits, especially when circuits become bigger, it's not easy to use nodal and analysis mesh analysis. You can use it all the time, but when circuit is really complicated, you will have too many variables. Yeah, it's not easy for you to solve system of equations with 10 variables or more. So sometimes we can see the circuit and with intuition, we find there is a symmetry inside, which makes us to make it more simpler. For example, see this circuit, you know, based on this vertical line, it seems everything is mirrored. Yeah, it has really symmetry. R4, R2, R3, R1, and E. What does it mean? It means the voltages in both sides should be the same. Yeah, that means I can have this circuit. Yeah? Make it half. We can have the half circuit here. Since C voltage and D voltage are the same, how much is the current here? It should be zero, yeah? When both sides have the same voltage, it shouldn't be any current. We have current when we have a voltage differences, yeah? Between A and B, since the circuit is completely symmetry, we don't have any current, and E and F, which means I can simplify this circuit with half of that like that. How much is current of R4? Zero, because it's disconnected that side. R4 doesn't have any current. We have one loop here. Okay. E over R1 plus R2 plus R3. These three are in series because we don't have any currents here. Yeah. E over R1, R2, R3. It's the current from this source. Yeah. Let's give more example. In this circuit, you can there is really symmetry in both sides, but the only difference is here we have negative voltage. Here we have positive, here negative, which means if I have 2 volt here, if I consider this node as a ground, if I have 2 volt here, how much I have here? -2. If I have 2 ampere here, current going up, I should have 2 ampere here going down. Yeah, there is a symmetry. That means if I have 2 volt here, -2 volt here, they are kind of playing differential, which means here are the 0 volt. Yeah, as a voltage, they are zero because if this side voltage is going up, this side should become down. I can consider all these nodes as the same potential, so I can connect them together. Do we have current here from this side to that side? Yes. Why? In the previous one, we didn't. Because there is a voltage difference between this side and this side. In the last one, if voltage here is 2 volt, here should be 2 volt. When across a resistor, you have 2 volt this side, 2 volt this side, which means the voltage difference is zero, so it shouldn't be any current. But here, if I have 2 volt here, I should have -2 volt here. That means there is a voltage difference. We have some current coming here. But I know since that's completely symmetry, it should be, these nodes should be the same potential. Because if this side is increasing, this side should be decreasing. So I can connect all of them together, and we have this simple circuit. How much is current of R3? Current of R3 is zero. Why? Because it's short circuited. Yeah. Current comes here. We know current prefers to go through the less resistance. Here it has zero resistance. So no current we have in R3. How about R1 and R2? No, R2 and R4. These two are parallel. We can consider them parallel because this side and this side are connected together. So this source is seeing R1 series with parallel of R2 and R4. So that's the current of the voltage source. It comes here. Can you say how we can calculate current of R4? I know this current, yeah? This is a current divider, like we saw, two parallel resistors. If I want to find current of R4, that means it's current of the source multiply by R2 over R2 plus R4. Multiply by this one. R2 over R2 plus R4. Another example, does this circuit have any symmetry? Is it vertical or horizontal? Can I consider horizontal? Why? Because there is a source here. But for vertical, if I put myself as a current wave coming up, I will see both sides the same. Yeah, the resistor in this side and this side. Yeah, which means we have a vertical symmetry. If I want to solve it with conventional nodal and mesh analysis, how many meshes do we have? 5. Yeah, which means I should write 5 equations, 5 variables. Solving system of equations with 5 variables is really tough. Okay, I consider a current here I. I know it has symmetry to both right and left side. So half of I should go to right side, half of I should come to left side. Okay, and from down, there is a current, we call it I1. Half should come from here, half should come from here. And again, I1 is coming up, half should go to the left, half should go to the right. Here we have half of I, here we have half of I1. What do we have here? The difference of these two currents. If you apply KCL here, we show all the currents and we just apply one KVL here, one here. It doesn't matter. You should apply KVL in two meshes. You cannot apply in these two meshes because they are the same. Yeah. One here, or here and here, or even here. If you apply KVL on two meshes, you will have two equations, two variables. Easily you can find I and I1. When you find I and I1, that means you find all voltages and all currents. How about this one? That's a cube of resistors. Do we have any symmetry? Kind of diagonal, yeah. If we apply V test and I test here, I comes here, it sees exactly the similar paths to go. Yeah, all three are the same. So it goes here exactly two paths which are similar. So if I apply VT and IT to here, IT comes here, it's divided by three paths. So 1/3 of these current comes down again. From 1/3, half of that goes to this way, half to this way. And here we have the IT here. Again, 1/3 of that is coming from each branch. And at the end, they are gonna come together and create IT. Is it clear or do you understand this one? You need just to apply KVL here. Yeah. Minus VT plus RIT over 3, RIT over 6, RIT over 3, and you will find the equivalent resistor is 5 over 6 ohm. This current is coming down. It sees two similar patterns. So it should divide it by 2. Yeah. Half of that goes to that way, half to this way. IT over 3 divided by 2 is IT over 6 here. How about this one? Same as the previous one, yeah? If we consider VT and IT over here, current comes inside exactly same passive, half of that to right, half to the left, and until the end. I only need to apply a KVL to one of these loops. We have IT here divided by 2, again divided by 2 until the end. That's uh, series. We need just to write the equation, and at the end we will find R equals to 2R. How about this one?
Can I interrupt?
Yes.
This tree that you see that is broken down has several different things. First of all, actually, when you are doing like RF design, that is big and one set, spread is combined, using that symmetry so that it actually splits three by. Let's say, for example, you want to have a power amplifier. If you want to have high power devices, one device cannot deliver all the power. So you actually use the big device. Use the big device in how you actually send the signal so that each of these devices that are supposedly in parallel see the same amount of signal and see the same amount of impedance on the other side so that they actually all work on the required this balance. If you don't do this kind of a strict kind of balancing, what will happen is that you see some of the devices are working and are becoming very hot, the others are not working. So on one side you appeal something expensive and then it starts breaking because the one that is under pressure breaks. So you have to spread that load, that pressure, which is the heat pressure and also the power pressure, the, the currents almost move them in a smooth way. So for that, you need to use these kind of structures to make sure that you can actually spread in balance. So this is one practical application of that. Additionally, these kind of problems is also helping our minds to become ready to reuse those concepts that we learned, basically how we actually can look at the curriculum structure. So it has a practical application in the products. It also has a practical application in our brain to fit the dots. Because I can imagine when you see a problem for a certain method, why do we need this kind of spreading of the resistors and things, and then at the end, okay, so saying this equivalent to one resistor. So say if you want to put one resistor, why do you need to have some resistor? It's the equivalent. But the reality is that nobody is down to if you can do something with one resistor, you do it with one resistor. But of course, that kind of spreading this kind of structure is very useful. Sorry for interrupting.
You're welcome.
To add a little motivation.
Yeah, thank you for explanation. Here we have another example. These resistors are parallel, yeah. If we have too many resistors in parallel, that means infinite resistors, we make them parallel. What would be the result? If I have two resistors in parallel, the value are the same. How much is the equivalent? The equivalent is how much? R? are, how do you calculate them? Multiply by them over sum of them, yeah? If you have 3, how much is the equivalent? Over, if you have 10, it should be R over 10. If you have unlimited number of resistors, it should be 0, which means that's only wire, yeah? They are short circuited. So you can consider this side as a short circuit. If we consider this side as a short circuit, we can write R, we have here 2R. If we draw this circuit, it's like that. Yeah. And it goes to infinity. Yeah. Which means the resistor I'm seeing from here should be the same from the resistor I'm seeing here or here. Why? Infinity plus minus 1 is infinity. Yeah. Again, it shouldn't, it's going to infinity. If you add 1 or reduce 1, it shouldn't affect the result. So I can consider these two. 2R parallel with R1 plus R should be equal to R1. Okay. That means here, shall I write this one or it's easy to understand? Yeah, I'm seeing R1 from here. That means R1 is parallel to 2R. The result is series with R. And this series all should be equal to R1 again, which R1 is R plus 2R parallel with R1. If we calculate this equation, we will find the value of R1, something like that. That's a second order equation, easy for you to solve it. Probably you have seen multimeter in the lab here. You used it to measure resistors, voltage, current. Yeah. But what is inside the multimeter? There is a galvanometer here, which if there is a current going across that, let me show you in the next slide how it works. When a current goes through galvanometer, there is it creates a magnetic flux here. Yeah. And when we have a wire which is located in a environment with magnetic flux, we have a one force over that. Yeah. It started to move a bit to the right. There is another spiral spring here which can cancel it out. In the moment these force and the force of a spring are equal to each other, it stops, which is showing how much current is going through that wire. And these are the polarity of the multimeter we have. There is a common jack that we use as a ground. The another one, you can connect it to different selectors. Yeah, you can select ampere, volt, O and measure each of them separately. Consider you want to measure a current. Yeah. You put this selector in ampere, common jack, and use this one. There is a circuit from here to here that's kind of short circuit. Yeah. It only measure the current. There is no resistor in the way, which means if you use amperment all the time, series or parallel with the circuit. When you are using amperment, you want to measure current. Series, you should watch. Yeah, it should be series because you can see there is no resistance that you add to this circuit. That's but when you want to measure voltage, we have different range of voltage. Depends on how much voltage you want to measure. You should switch between these resistors. These values are usually a big numbers. Yeah. And for measuring resistance, we should change the selector to this port. There is an internal battery which comes from through a internal resistor, and you connect your resistors here between these two. Yeah, which means if I want to show you the equivalent circuit of measuring a resistor, suppose we put the selector in. Oh, we connect the resistor that we want to measure to this and this jack. So we have this resistor that we are looking to find here, which is connected to here. We go through this and this battery. We have one battery here, and if we write the current which is go through this, we have one small resistor here and galvanometer resistance. That's so small. Yes.
Have a way that we can measure current from a branch, a branch, without cutting the branch or putting something in it. So you have a circuit without touching it, without breaking into it. If it's DC, then you think of a way to measure the current in that.
When you are using multimeter, you need to disconnect a wire, put the multimeter as series. Yeah, you cannot connect it as a parallel. Yeah.
The
Yeah,
voltage you can always connect from the two sides. You don't need to change the circuit.
that's parallel. Yes.
Again, I decided to jump in here because I know you guys like practical. So these are practical problems that we always have. Measuring voltage is usually easier. Just put the thing in. Measuring current, that means you have to pre-plan putting something in between or leaving some opening. Let's say, for example, you are designing a circuit board and you are not sure that whether the current there is going to be exactly what you want or not. And if that current is sensitive, you need to check it. One of the easiest way would be to either create connectors there and basically put a short resistance in there. So when you want to connect, you short it. So you don't, when you want to test it, you just remove that resistor. Then you open it, then you can put your ammeter on the max. So you create your short with the ammeter to measure. But it's hard. Yes. It's important that you understand that you need to be in the circuit to measure this. If you want to measure it precisely, for sure. But can you think of a way to measure the DC current without being in a circuit? By using the own relationship, they have the but you don't know what is the resistance. How can you know that? Let's say, for example, you say this much resistance, but if it's different, or if some IC is there, and then you don't know what is the behavior. So someone in this now usually have something like that. I believe it's form of electromagnetic field. Even more of this. Some of it can be done because you can actually measure. So one of the ways would be if you can measure the field across the cable. By measuring time, you can get 100 meters on how much current you have. Because every current is an activity. But that's not very precise. So if you want to do precise access, if it was AC, because the coupling is much. That's one of the methods. But anyway, it was important to remember that you need to be able to be in the path to really measure the current. And whatever you put in the path for measuring the current has to have very low resistance. Because if you change the resistance, then you're changing the current. That's why ampere meter has to have zero resistance. Theoretically, ideal ampere meter has zero resistance. Ideal voltmeter. Yesterday, Professor taught us about Thevenin and Norton equivalent circuit, right? The voltmeter needs to have what kind of impedance? In your okay. So this one. The voltmeter, what kind of resistance does it need to have? Ideally. Infinite. It has to be open. So when you connect it, it doesn't change the circuit. But if you add any resistance in parallel with the circuit, you're changing the overall resistance behavior. But if you put an infinite resistance in parallel with anything, nothing can do. Why? Because you have two resistors in parallel. Let's say R1 and R2, right? So if 1 over R1 plus 1 over R2, then 1 over coulomb becomes the total. So if R is infinite, 1 of R2, 1 over R2 is 0. That doesn't change anything. So we want to add something in parallel, it has to be very high. You want to put something in series without changing anything, it has to be very low resistance. Right? So that ampere meter has to have very low resistance when you put it in a circuit. When you want to use it in the voltmeter option, it has to be very high resistance. That's why even when you have a multimeter, you have to actually switch between the voltage and the current. And actually the input for the voltage board is different than the input for the current. Because they cannot have both, you cannot have both infinite resistance and zero resistance in one circuit. Right? So actually, one of these theories, when you start going to the lab and using even as simple as this, you start seeing that it's actually working. It's useful. Sorry to interrupt.
You're welcome. When we want to calculate a resistor, we want to measure a resistor that we connected to these two probes that we have. We have one probe here and another common probe. When we want to calculate the resistor, I can write it as a Rx that we don't know. So easily there is a KVL here. Yeah, if you write a KVL here, you have this current I is VB over RO plus RX plus RG. It, RX is unknown external resistor. We are going to measure this one. Yeah. RO means the internal resistor we usually put to limit the current. And RQ is internal resistor of galvanometer. Yeah. This current has a limitation. Yeah. It can be zero. You can put RX infinity open circuit. Yeah. But uh, it cannot be too much because of the full scale range of the galvanometer. Yeah. It should go to full scale range, which means we have an upper limitation for this current. Another measurement circuit that we use for more precise measurements is Weston bridge. Yes. As you can see here, we have four resistors connected like a bridge together. When it's balanced, R1 should be equal, R1 multiplied by R4 should be equal to R2 multiplied by R3. Okay. What will happen if it's balanced? We don't have any current here. We use it to measure, for example, R4. One of these resistors, we can change it. They are changeable resistors. We change it until we see there is no current in the galvanometer. When there is no current in the this galvanometer means we can find R4 or Rx that we are looking for from this relationship. Yeah. Why is more precise? It's independent of, you can see, there is no independent voltage here. Yeah. Your battery may decrease with aging when time goes, when time passes, it can be degrade and its voltage can drop. So it's not, it's independent of uh, voltage source or your battery. This current, we only need to find there is current or not. That means we are limited to precision of this galvanometer. Yeah. We don't need to scale it, so we can just measure is there current or no, which means this is more precise than scaling the whole uh, measurement range. This this is more precise the multimeter measurement that we had, and its application usually for sensors and string gadgets. Let's see this example together in which how we will find the difference in precision of these two circuits. Consider we have, I think I gave you this one as an exercise. Let me check. Yeah. Okay. That's kind of exercise. You need to think about that, how you can calculate and find the difference in precision of these two circuits. We have a Watson bridge here and a multimeter here. We want to measure a resistor. For analog multimeter, we have these parameters. Its full scale current for galvanometer is 50 microamp. Uh, there is a 3-volt battery, or 50K. Uh, galvanometer resistor 2K. For Western bridge, we have R1, R2, 10K, R3 between 0 to 1K with a step of 1 ohm, and we are going to measure R4 with a 5-volt voltage. Okay, for this one, how much is the minimum and maximum resistance that we can measure? For this one, that's the resistance I want to measure. Yeah. How much is the maximum and minimum of Rx that I can measure? Okay, you can say we know the current should be like this. Yeah. How much is the minimum and maximum of this current? Infinity. It can go to infinity. You know, you have a range on the galvanometer. Yeah. It starts from here and it has a one full scale range. Yeah. Depends on the current goes through that. What's the maximum value for the current that it reached to the full scale? We have 50 microamp. That means this current should be between 0 and 50 microamp. So VB is 5 volt over our 3 volt. 3 volt over 50K, 52K plus RS, 50 microamp. We can reverse it. 52 plus Rx over 3, 50 microamp, multiply by 3. Oh, wait. It should be 1 over 50. We can write it 60 is 8 kilo ohm. Which 8K. Yeah. which means we can measure Rx4 higher than 8K, not less than. Am I wrong? Right? I should go up the which one is bigger than the small and big notation, yeah? It should two is bigger than one, yeah? How about if I reverse which one is bigger? If I reverse this to fraction, power of no. I just uh reverse the fraction. I just reversed it. I didn't do anything.
Let's say if A is less than B, A is less than B. If you want, if you actually say 1 over A is bigger than this one. So it basically, if it was less than, it becomes greater. If it was less than or equal, it becomes greater. That's what you did. So that's what you have to do that, right? If you have, let's say 10 is greater than 1. 10 is greater than 1.
I minus 52 in two sides. That means Rx can be 0. No.
Well, before that, you can refresh your algebra. Actually, nothing that you can go to ChatGPT.
I multiplied both sides by 3
On all the algebra.
and move and uh, reduced 52K from all sides. Here is 0 minus 52K.
This time you will get because this one you're looking at it with intention and without intention.
It shouldn't be 8K. Wait, it's 3 over.
You didn't expect that.
Yeah, 8K.
Use it. Whatever you learn now, 20 years from now, whatever you will do.
Mm,
So is this finished?
Um,
Do you have any questions?
no, I need to.
Or anything for something else?
Yeah. I think I made a mistake. Yeah, exactly.
And the lesson again is
Yeah.
either find that you have understand that you have made a mistake, try to find it, or when somebody tells you that you made a mistake, instead of thinking, oh, I don't make this, figure out. Let's try.
Okay, let me write like that. I think that's better. It's better.
Are you going to calculate it?
We have a multimeter here. We are looking to find the range of Rx that we can measure.
How much? Okay, what is the maximum resistance you can measure? What is the minimum?
Exactly.
Right?
Yes. What we have in internal circuit.
But before going into the calculations, can we measure zero?
Depends. If
In that range that the full R3,
yes,
right?
we put
In the ohmmeter mode, right? You are in the ohmmeter mode.
here. Yes.
Okay.
We have RAG for galvanometer 2K and 50K, the internal resistor of the multimeter.
So can you measure zero? I think you can,
No.
because that's the minimum that is shown, right?
We should set the minimum of, if we measure Rx equal to 0, we have current here, we should adjust that current as a minimum of the galvanometer current here. That's
So in old times, when you would
that's
see analog multimeter, and actually analog multimeter are much more precise, even today.
yes.
Using analog multimeter, you have to come back to the month.
If we put Rx 0, how much is the I? I would be 3 over 52K, which is
This problem
almost 3, 1. Okay. Can we measure the Rx equals to 0 in this circuit? You know, if we put Rx equals to 0, how much is the current going through this circuit or going through the galvanometer? It should be around 60 microamp. What is the full range of the current of full range of galvanometer? 50. Which means if we short Rx to 0,
cannot give you enough current.
yeah, we will go out from the full range. How much is the maximum? How much is the minimum resistor we can measure? 8K. How did you calculate it? Yeah, we can consider this current. The full range should be 50. It should be 50 microamp, 352K plus RA. So RA is 8K. This means the minimum resistor we can measure is 8K. And if we increase this resistor to infinity, this galvanometer should come to its 0 current. Yeah, so that means it should be from 8K to infinity. That's the range of resistance we can measure. How about with Whetstone Bridge? We mentioned R1 multiplied by R2. R4 should be R2 multiplied by I3. I'm looking for R4, R2, R3 over R1. R1 and R2 are 1K. I can simplify. It should be R2. I can measure exactly from 0 to 1K by a step of 1. Oh,
So did you remember what you need to have for a Western bridge to be balanced? What it needs to be for a Western bridge to be balanced? So basically, if you look at this as the voltage divider, whatever it divides the voltage of C is equals to this D, then that's you measure zero. It's very useful, in particularly in the old measurement tools and also for any measurement tool, because measuring zero can be very, very precise. If you want to measure any number, it depends on the scale. But when it comes to exact zero, so if you have a sensitive and voltage meter, you put it there. You know when it's zero, it's there. So you know you cannot have any error detecting this. Any other number depends on where your scale is and whether the scale is shown properly and is it calibrated or not, right? But zero doesn't need calibration, right? If you disconnect it, it's where it is. That's your zero. So then you can very precisely see that becomes to the zero. So if these other values are proper, then you can actually, so basically you have three of those resistances, you can know the fourth one. That's one of the things. But if you use many different measures. In general, the philosophy is you try to use the particular area that you try to do the measurement, you want to use something that has the least error. And measuring zero voltage, if you have the bridge, can be very, of course, not measuring in the air. If it can show, if it can become negative and it can become positive, and then you can manage it to show zero, that's a very precise way of measuring. That's why this Western bridge has been very used way beyond any other invention. That's a very simple thing.
okay. And how much is the smallest resistor that we can, that means the sensitivity that we can measure with these two measurement tools? We found it. When we are measuring 100 ohm, how much is the sensitivity of the multimeter we calculated? Can we measure 100 ohm with this resistor? We cannot because of the internal resistors. We can, it should be the minimum is 8K. How about this one? How much is the sensitivity of this one when we want to measure 100 ohm with Western bridge? You know, the relationship is R4 is equal to R3. What is our precision to control the R3 step of 1 ohm? That means we can control R1 with a step of 1 ohm. We can measure it with the resolution of 1 ohm if we ignore the precision of galvanometer.
What are the other topics?
What did we see? We
How much more time do we need today?
we already passed. We already passed 20 minutes from.
I also have a
We
suggestion.
talked about. Uh, I gave another good example for calculating Thevenin and Norton. They became familiar with this one kind of
So I have a
transfer.
suggestion. You don't have to accept it. Of course, professor has to act. But my suggestion to make the class a little more fun, the next session, which will be inshallah on Sunday. Give the slides, all the slides that for the lesson, that all the slides that are left from today that we haven't finished yet, and the ones that has to be covered on Sunday.
No, we finished these chapters, and after that, we are going through RC and RL circuit.
So those slides that we should cover on Sunday, how many slides are there?
Let me see. 4. This is chapter 4. How many are there? 41.
41 pages.
Yes. And chapter 5. I think chapter 5 is less, maybe 20, something like that.
We have
16. Yes.
How many of you are here? Take each of you become the teacher for 6 pages. You can. At this stage in your life and your education experience, you actually can be the teacher. What you need to do is to go and study those pages well and come and explain. Of course, we are here to cover for whatever that is missed on you do that. And so we have 10 sections, each of them, let's say 5 minutes, that becomes 50 minutes. And then we will be having the rest of the class, 1 hour, 10 minutes for us to cover the gap.
Yes.
So that would mean each of you who are here are going to study all of this first of all by yourself over the weekend. Prepare your pages that you have to be the teacher even better. Practice how you're going to present it. And let's see if you can make it exciting as well. So I want to see your creativity on how you will make the class more exciting. Because one thing is when you sit there listening and sometimes you lose attention, sometimes you don't find it exciting because your mind is not completely there, or you know all of that. But if you come on this side and try to grab attention of your classmates, that's a competition between you. Then at the end of the day, we will make you guys vote see among everyone who was the best teacher. That's also going to be very useful for your career experiences. Do you agree to do that? This means Taslim, you say yes, or this means Taslim, you say no. No, you don't do it. Taslim means you say yes, right? You don't do it. So we cannot make it that everyone teaches a little bit, huh? Anybody volunteers to do that?
We can ask in the group and see who is volunteer.
Yeah, you can ask in the group. We like to get volunteers. The more of you, we appreciate you becoming volunteers. Definitely coordinate with Nisha and Professor which pages. You can even, if you like, you can practice going through it, recording your voice, sending out, you will listen. 5 minutes, nothing. Why don't you go and no, first of all, we don't want to force anyone to attend. Anyone who doesn't want to attend. What we want is we want to encourage the ones who attend to succeed even more and benefit from. Remember, at the end, I am looking on one side for moment. We have a couple of agendas. Agenda one, I would like to do something that is inshallah good for all of you. Having some impact that say next to all these other courses that you have learned and things. This was an experience that helped boosting you in your career or your way of thinking or problem solving. That's what. But for morality, we also like to identify who are the best likely colleagues that we want to have in the company that we can invite them to join us. I like great people. I like people who like problem solving. I know sometimes you are shy talking in front of people, right? I give you the simplest way that you can have confidence in talking in front of people. Imagine you're talking to a number of bats. When you consider your audience human being, it creates tension for you. You're worried. What is their perception? What you respect, but the reality that worry is not necessary. Okay, what's wrong? If I say something that is not correct, it's wrong. What happened? You can correct it. You can tell me, oh, say, Andy, what you said was you had a mistake. Not the end of life, right? So you have to build your confidence, overcome your fear of doing public speaking and teaching. You can do it. And I ask you to now bring it down there, or you don't want to resist. You are free to resist. I respect it. Before I would see this. Okay. So it's only for volunteers. Don't worry. You want to see what? See slides. If you like, volunteer. If you do not volunteer, we will not say why you didn't volunteer. We will not blame you. It's okay. You don't have to if you don't like to. But I like to encourage you to consider doing. Because even as engineers, as professionals, you will have to present your work. You will have to talk to people and explain. You will have to interact with customers. Right? If you go sit down in front of customer and you know that your the earning of your company is dependent on the customer, if you start shaking and getting worried that, oh, what if I make a mistake there, right there you already have lost it. So others are people like us. We should like them, we should respect them, we should try to be genuine, we should try to explain, we should try to hear them. But you shouldn't be afraid of them. So it's a good practice. Even if you don't want to do it for this class, do it sometime for yourself. Don't be afraid. You don't have to do it, don't you're not imposing. But I like to make the class more fun. Yes, it's not a punishment for those who come. It's an encouragement for those who come. Okay, I hope you see that. We appreciate that you are doing this. Pay attention. Thank you. Any question? Um, so, yes. So have you been solving problems that they are giving you? Or the assignments? Yeah, homeworks that
Yes.
they give. Have you been solving? A lot of questions.
Yeah, that's why you need to practice and learn. Yeah. If you learn this part really good, I assure you, after that, life would be really easy. Yeah. That's the most important part. You should learn really well.
Of all these other lessons that we will be doing, basically there are three foundations. One is this circuit, the other is electromagnetic. The rest of it, electronics, those things are easier once you are good in this. Because it's basically the same concepts are being used in understanding those networks. So it will be reviewed to get better and better. If I end up, even when you sit down and do your exam and this, you see that you have some weaknesses on some of the areas of it. It's okay, so long as you keep reviewing them and solve those problems for the next like month, 1 month, 1.5 months, your foundation will be studied. And you will see that the very same things are used in the electronics portion as well. And then you can use it for it. So there is no deadline. We like to recover this. So if you need a little more time to do that, it's okay. Yeah, we do the exam. We do one exam next week. So we need to see how far you have come, how far you have come. And there we go. So that we also understand where the weaknesses are. We see where the weakness is in certain areas. Like you remember yesterday when we were going to calculation of the level. Based on your question, I realized there was one potential weakness can be, so I started breaking it. So from computer exam, we will understand where some of the weaknesses are. We may come up with some sort of remedy that way to help you overcome that weakness. And the whole hope is to minimize the weakness point and to also know where the weakness points are. You know where your weaknesses are. We also know where your weaknesses are. And then if you like, you can figure out how to tackle it later. You have a long life and you will overcome all your. When the exam will be in which date? Thursday is holiday, right? So next week Wednesday. So next week Thursday. Yeah, next week Wednesday. Thursday is holiday. Thursday is first of Muharram. Ah, okay. So to be Wednesday. So let's do it Wednesday. What which topics to cover? The circuit design. Only the three shop or the no. All the chapters you need to have that. Can you please? Yeah. And is that after the holiday? It can. The thing is that I will not be here this Sunday after the holiday. I have to travel. I would have preferred to be here to help you on the exam day. But the purpose is not for you to be intimidated. It's a matter of understand. Exam is a measurement. Yeah, you see, we do the science of it, then we model what happens, then we measure. Then say, okay, what is off, what is going and fixing. We feedback again. So this exam is not to fail anything. The purpose is to measure. The better is more useful there the level is, what is missing, how we can cover it. Yes. The question is like
Maybe 7, 8. No, 7, 8, but they should have different ones.
7, 8 questions.
Doesn't have ABC.
Probably. We are gonna assess all parts that you learn, yeah? For that, we need to give you too many questions to assess all aspects of the topic.
The telescopic thing, you can keep solving and go forward. Some people will do more, some people will do less. And from that, you basically get the diagnostic and you get the diagnostic. What are the things that you already know and what are the things that you don't?
And they're looking every or it's all the solved and closing.
But it means here, and we are not going to ask you these 20 questions, saying, okay, what I'm trying to do. It's going to be a problem that you have to solve. But approach is important. Like, for example, if you struggle with your algebra, you solve it. So long as you write the equation right and show that, okay, this is the equation that I'm going to solve, and you see that of course, at the end, you see that you can get the right last number of a final number. Yes. What about the derivation of the place? How long do you write it? 5 hours, 10 hours, 2 hours. Depends on the question. I would say on Wednesday when you come, please have your schedule in a relaxed mode so that if you want to give you more time, you can. Ideally, I would say, okay, you have the whole Wednesday to solve it. Whenever you want to give up and go. Is that good? But we don't add time pressure to it. Does it make sense? What about formula?
No need. What do you need at the
Formula sheet? Yeah,
nothing is needed.
you can have all the slides.
Yeah, you can.
You can have all the slides.
Yeah, but it's not gonna help.
No, you don't want to test your memory anyway, but you have to memorize in order to be able to solve the problem.
Yeah. You really won't need it.
If you do the homework, you will be able to go do the exam. If you don't do the homework, it's going to be like sitting there in the exam trying to do your homework. Even if you do something the first time, it's hard. If you do it the second time, it's easy. Homework is there for you to do it the first time. But definitely you are in the exam, you're doing it almost the second. For the good bad. So they can have all the slides, right?
Sure.
But it's more than 4 million sheets. You have all the slides. Pardon me? Open notes. Your notes, your personal notes, you can have it as well. So
That's why, because if they want to have this, that means they want to have phones. I don't know, maybe.
You can print slides.
Can we
Our items. You want to have ChatGPT solving it for you.
That's why I think
It's
we don't need any.
Oh, no, you have the slides. You know, even if you can solve it with ChatGPT, fine. Let's modernize. You should be able to come up with the right answer. But then You will limit the time. Which way do you prefer? You want to be able to show your foundation knowledge and you look at it, see whether you have a foundation knowledge, or you want to come up with the right correct answer. Yeah. Remember, there is no value in developing sheets or classes for ourselves in this particular thing. You don't have to take this course. You're taking it because you want to learn. So if you create a bypass, you're creating a bypass for yourself. Then you have to keep thinking, why did I take the course in the first place?
Oh, I didn't.
Right? So this is not a university course. Say, oh, I need to pass it because I need to get my degree. So no choice. What the hell? I'm using ChatGPT to solve it, get my degree. This is a voluntary course. You didn't need to take it.